Hey, let's talk technology and sports science. It's such a fun topic because there's a lot of different technology that we can have access to and use when we're doing sports science, not only in what I call our bricks and mortar lab, our building on campus type of lab, but also when we go out in the field and we test athletes in their environments, on the playing field, on the court, what have you, in the pool, what have you. And so it's really neat to see how much technology has become involved with sport in the real world. Now we are in the sports science, and I never want to lose the focus on the science part of sports science. And when we start talking about technology, we have to be careful not to just talk about being able to operate equipment. We don't want to be technician. It's not sport technician. It's sports scientist. And so we really want to understand the scientific method. And we want to use different instruments to collect objective information about some aspect of sport. And then measure a whole bunch of things. There's lots of different measurements we're going to make, and this is just some sampling of some different data that we've done. But the key is not only to measure stuff, but we want to be very purposeful when we're doing our measurements, because we want to take in a lot of the different information that we get from a variety of instruments, and we want to generate knowledge. That's really what we want. We want sport knowledge. And we want to use that sport knowledge based upon science to understand athletes right now. And we want to help over the long period of time. And we want to continue to work on generating knowledge about the science of sport. Okay, so that's sort of the framework that we got to keep in mind when we're talking about sport technology. And the other framework I always like to come back to, because it's so easy to start, looking at technology and all the different options. But we want to keep in mind that what we're trying to do when we're using technology is we're trying to help our athletes move into the healthy high performer quadrant. I've presented this model before. Health is on the y-axis, performance on the x-axis. And we have healthy high performers, we have healthy underperformers, we have unhealthy underperformers, and we have unhealthy high performers. These all exist. And maybe you were in one of these quadrants or multiple of these quadrants, even in your sport career. And I'm also trying to be careful when I present this type of model that I'm not only interested in the elite athlete. High performer may actually mean for the age grouper completing an event, because that's their goal, versus someone being able to jump as high as possible and break a world record. Okay, elite performers are, that's amazing. But I don't want to lose sight that this model does also apply to our everyday athlete. And how do we help people be healthy? And how do we help them perform to their highest ability, given the constraints and the context of their lifestyle? Okay, so this is not just about the elite performer. This is about the everyday athlete as well. But when we start talking about technology in sport, technology in sports science, what we're using technology for is to help us move people into healthy high performer quadrant. Now, all the technology, there's a lot of different options out there. In fact, we recently published a paper on a model to follow when trying to select technology that would be applied, in this case, to doing some circus artist assessments. And so we've gone into this direction. We're trying to help with circuit athletes. And being in Vegas, I mean, it's just so Vegas. The shows that are the different casinos are staffed, and they have elite athletes doing the performances. And those elite athletes are performing a little differently than in a competition, because they're not being judged, they're not being scored, but they're doing their performances at a high level for aesthetic reasons, for choreographic reasons, and for audience, pleasure, if you will. And so, with our interest in trying to help these athletes, because they do get injured, and they have the same issues of being careful about reporting their injuries to coaches, to staff, what have you, because they don't want to lose their job. Just like an athlete doesn't want to lose playing first base or their spot in the batting order because of an injury. And so there's a lot of commonality between circus performers, circus artists, and athletes in team sports, individual sports. And they still have to train, they still have to practice, they have all that, and they get injured. And we're interested we've been interested in trying to quantify the kinematics and kinetics of some of the movements, but the movements are so unique. It's not like throwing a ball. It's not like swinging a bat or a golf club. They're very unique, and there's just some picture of some different acts, if you will. And trying to quantify those acts is not easy. And so we went down the path of trying to do that, and we've tried out different instruments, and eventually said, hey, you know what? Let's just share what we've learned about trying to pick instruments to measure circus performances. Okay, and that's what we did. We put together this paper. Dr. Lena Swafford, Nate Hollister, she's currently a postdoc with us. Nate Hollister is an MD who's a previous circus performer. Scott McDonald is a current performer and coach, and then myself. And we just put down a lot of different things that we were talking about when we were assessing different instruments to try to use to quantify kinematics and kinetics of circus or circus acts. And so we came up with this model. We needed to understand what type of data were required, that we're trying to get the device accuracy and reliability, that's critical. There's a lot of instruments out there that have not been tested. The validity of them, the reliability of them have not really been established. Comfort and fit is very important, especially in doing the circus maneuvers. Often, if we are measuring during a show, we need to be careful of how the instrument works with the costume. Cost and availability, that budgets are always something to keep in mind, and whether or not instruments are available. There was times that we've pre-ordered instruments because they weren't quite available, but we really wanted to get first access to them when they did become available. Durability and battery life, this is important for, again, if we're doing shows or we're doing practices, it may be a sustained period of time that people will be doing certain maneuvers. And the durability, the different acts, some of them involve a lot of contact, trampoline type work, bouncing on instruments, how well will these hold up over time. Data accessibility and processing, we typically want to be able to get access to the raw data. Each of the instruments that you can buy come with some proprietary software to process the data. That may be helpful for certain analyses, but when we use proprietary software to process data, we often scratch our heads and say, wait a second, what's happening in this black box of processing? Because there's a lot of decisions we have to make when we take our raw data and ultimately get our data that we communicate to an artist or a coach or what have you. And so there's a lot of steps involved with that. And if we're using proprietary software, we don't often know what those steps are, what algorithms are being used to process the data. And so we typically, when we look at instruments, we want to be able to get access to the raw data. And then we process the data independent of the instrument. And then integration with existing systems. Often we want to use different systems, but we need to get them to synchronize with each other. We need to get them to talk to each other so that when we're looking at the data on a time axis, the time axis is the same for each instrument. Sounds easy, but it's actually a little complicated. Each of these instruments will have a different way to trigger it to start. And they will have different sample rates, how frequently they sample data, and what have you. And so we have to consider all these things when we're trying to measure a particular act and when we're trying to select an instrument for what we're doing. And also when selecting instruments, we need to think about the big picture in terms of how the body moves. And we need to consider the chemical energy in the body, the potential energy in terms of our macronutrients, our carbohydrates, fats, proteins. We need to understand our energy systems, where we're transforming the chemical potential energy over to mechanical energy. We need to understand aerobic and anaerobic systems and which one may be dominant in certain maneuvers, and whether it be artistic or now for even being more broad in terms of sport. And we need to understand the mechanical energy. We need to understand kinetics. We need to understand kinematics. We need to understand how forces are causing movement and forces are applied at a particular point, in a particular direction, a particular magnitude, and at a particular time. And all those things we need to understand when we're selecting an instrument. Sometimes our instruments are more focused on the left side of this model, sometimes the middle side of the model, and sometimes the right side of the model. So getting more specific to some instruments that we use, I'll mention the Speed Lab again, Sport, Performance, Education, and Economic Development Lab. This is our mobile lab where we have a wide variety of portable equipment that we can take out to the field. And we can take to a soccer field, we can take to a football field or a basketball court, what have you. And we can employ those instruments to measure athletes in their environment. And that's becoming more and more important because we've done a lot of work in our bricks and mortar lab or building, but trying to move those measurements out into the real world is a really important next step in sports science. And anytime we start making equipment smaller and more portable, we're giving up something. Sometimes it's accuracy of the instrument, sometimes it's durability of the instrument, and what have you. But we are very careful in picking the right instruments for the type of work that we want to be able to do. So I'm going to go through some of them. VALD is a particular set of instruments that we use. And right now we have a hand grip dynamometer. We have force platforms. We have force frame, which does isometric strength measurements, and we have timing gates, for example. And these are important. And a lot of professional teams and collegiate teams are using this system. So it makes a lot of sense if you're interested in sports science, get involved with the things that we're doing, because then you can have some hands-on experience with working with these instruments, how to operate, how to collect, different questions that I've already talked about. What's the sample rate? How do you get the raw data? What does the number mean when it comes up on the display? All those things. So very, very common set of instruments. Our professional teams here in Las Vegas, Vegas Golden Knights have a system. The Raiders have a system. And I'm not sure who else after that. And then our collegiate teams, UNLV has one, has a system, and as well as us with the Speed Lab. Another set of instruments we have to measure kinetics, and kinetics is the branch of mechanics dealing with forces that cause movement. We have some load cells, or some force measuring cells that we put inside a shoe. And this is really nice because this is portable. We can measure the data on an iPad, and we can have the person doing all sorts of things, from running outside, running on trails, or wearing these inside shoes during a circus act, what have you. And these are very helpful. The trick is we need to have enough sizes of these to fit into a wide variety of shoes. Because once you cut them to a certain size, that's it. If you have a size 7, you can't make it a size 10. And it is important to watch the durability of these. There was an earlier version that we had, a different manufacturer, where the insoles were not very durable. We could barely get through one data collection with them. And so that was a system that really wasn't practical for sport application, because the instrument just would not hold up in real life. And I put this here too. This is just another example of a load cell. This is a force transducer, an inline force transducer, and you pull on each end of this sort of S-beam. And what we're using that for is to measure the force in line during a hair hanging study. All right, sounds simple, but what is the force that's exerted to her scalp? And we're partnering again with the MD I mentioned earlier, Nate Hollister, to measure via ultrasound some of the tissue changes that are happening when doing these types of acts. Going into the branch of mechanics called kinematics, that's the study of motion without really concerning ourselves with the forces. Yes, they go hand in hand. But kinematics is focused on what the movement looks like. So we use a lot of video. We use some different devices like this one right here, which is an inertial measurement unit, IMU. And IMUs are combinations of accelerometers and gyroscopes. Accelerometers measure acceleration, rate of change of velocity, and gyroscopes measure orientation of the accelerometers. And through the combination of those two instruments, we're actually able to get really good information about kinematics, how someone moves. So in this case, this is baseball, and you put sensors on segments. This is a cartoon of this, but we will put a sensor on the upper arm, on the forearm, maybe on the bat, on the thigh. And then from there, we're measuring the acceleration and gyroscopic information, and we're getting a 3D model of the person. Really fantastic unit. And this technology has really been refined over the last 10, 20 years. And it's really become very useful out in sport because we can put these sensors on someone and do a wide range of activities. Another set of kinematic tools are markerless capture systems. And I say markerless because we're not actually putting anything on the person, and we're using this 3D camera setup. And that camera setup is using image processing to ultimately identify segments of the person. And then this is in 3D. So I'm only demonstrating a 2D image here, but 3D means we can rotate this image around just like the previous one as well. And 10 years ago, marker systems were really what we were limited to, meaning we would put little reflective markers on specific anatomical landmarks. You probably have seen commercials from different video game manufacturers where they have an athlete with all these little stickers and all these reflective markers on the athlete. We do that work in our lab. Highly accurate, very good system. The challenge of using a system with markers is you can't really use that during games, and maybe not even in practices if there's even contact. And sometimes with sports that have high accelerations, the markers fly off, and once the marker falls off, we lose all our data. So the advancement of markerless systems has really been tremendous. Really, over the last 5 years, I've seen a big change in these systems. And it's really impressive to be able to set up the cameras and be able to make these measurements. The trick is with this system, it still is not really ready for game time because here's a camera here, here's a camera here. It's in the play field. So we still have some limitations in terms of of how the system can be used or when it can be used relative to sport, but definitely for practice and definitely outside and, in this case, on a baseball field. Switching over to physiology, there's a lot of portable systems that are being built. We always have heart rate, and I'm sure you have heart rate on your watch, or maybe you have a chest strap heart rate monitor, whatever it is. And heart rate has been a sort of a mainstay of a lot of field work to understand physiology. And the reason for that is this set of data over here. This is from a single subject doing a graded exercise test. This is VO2, rate of oxygen consumption, on the y-axis and heart rate on the x-axis. And it turns out that heart rate is a really good predictor of rate of oxygen consumption during aerobic type exercise. Sprinting, weightlifting, totally different. Watching scary movies, totally different, okay? But when we're doing continuous exercise, heart rate ends up being a fairly good predictor of VO2, and that's why we've used heart rate out in the field for a long period of time to measure something like exercise intensity. Rate of oxygen consumption is really what we want to know, because that's telling us what the intensity is and how active the aerobic system is. Well, more recently, 5-10 years, again, that window, we've seen advancement in portable VO2 systems. We have VO2 systems in the lab. They're hooked up to computers. They cost $50,000, $60,000. Well, now some of these systems, well, they can still be quite expensive. This system here can be up to $50,000, maybe even $60,000. This system here is down around $10,000, $12,000. But in both cases, they're portable, and the sacrifice you make in price is often how accurate the data are for certain intensities of exercise. So there's limitations with everything. And you have to examine the limitations of using a device like this versus a device like this versus someone coming into the lab. The lab is our gold standard for measuring VO2. Once we start getting portable, we're getting much better accuracy with the instruments, but we're still, this is still in the works. And I'm really encouraged by even smaller devices like this, because now you can envision wearing this in all different types of activities, cycling, running, bowling, whatever it is. You can start measuring VO2 in much more dynamic. Even our circus movements, it's easy to put this on someone where that's all it is versus even having a unit that's strapped to the back. You really can't do a lot of circus movements with this type of device on the person. So again, we're trying to get to VO2. Sometimes we can only get heart rate, and that's a limitation, and it's heart rate's only a predictor of VO2. Physiology, I also do a lot of work with core temperature, and the advancement in core temperature is really pretty tremendous. To get core temperature, you take a thermometer or you put something in your ear or what have you. In the lab, it's a rectal thermometer is the gold standard. Well, this thermometer right here, this pill, which is smaller than the size of a quarter, it's like a big vitamin, that's an ingestible core temperature sensor. You swallow it, and once it goes in the system, it's starting to monitor your core temperature. Now, we have some guidelines in terms of how long we want to have it in the system before we start monitoring, because it has to go through the stomach, get into the GI tract. Once it gets into the GI tract, it's really very stable in terms of the core temperature it's measuring. They are single use, so they just pass through you. We don't actually collect the pills again, but we do. We can scan the person to see if the pill's still in them. And so we actually did some work on core temperature swimming in open water in a wetsuit. And so this is just a map of the swim. Person swam basically 700 meters down and back, and we measured core temperature during that 700-meter swim. And these are just some data from that. I'm not going to go into detail with this, but core temperature is on the y-axis for each of these, and time is on the x-axis, and then we have two lines plotted for two data sets plotted for each quadrant here. One is for no wetsuit, and the other is for a wetsuit. And then I've got subject 1, 2, 3, and 4. And the reason why we're plotting each subject by themselves was to show how individual the core temperature changed during the swim. And so this is the this is the wetsuit condition. There's no wetsuit condition for this subject. That looks quite different than this subject. And that looks different than this subject, and even this one. So each of these are very unique. And so what we're actually doing here is calling attention to how to use this portable equipment. And we need to be careful with understanding how different people will respond differently to these swim conditions. And it's not enough just to average the data from start to finish. We actually need to understand what's going on with this core temperature dropping and increasing. And so there's a lot of unique things that we need to sort of still dive into to understand how core temperature is changing during the swim. Body composition, being able to measure body composition has gotten so easier. 15 years ago, 20 years ago, we were using an underwater weighing tank, which was the gold standard. And that's great. You had to weigh someone in the water, underwater. And the idea was that fat floats and everything else sinks. And so if you can weigh yourself in the water, you can get a sense of how much fat you have just based upon some buoyancy equations. And that's all good. You do have some limitations to that. And you do have air in your lungs that helps keep you buoyant as well. And so you have to try to exhale all that air, or you have to measure the residual volume in the lungs. And so there's always some limitations. And it's hard to do underwater weighing outside of the lab. So this company and others have come up with bioimpedance instruments where they send a little electric current through the body. And by measuring how long it takes that current and different frequencies of current going through the body, they can determine how much body composition, how much body fat, how much muscle you have, how much water is in the system. So really pretty slick instrument. They've gotten more accurate over time. And right now we actually have a portable system that we can take out to the field, as opposed to a system which we don't really like moving the ones in the lab around a lot, because they are sensitive instruments and we don't want to bang them up a little bit. But the portable one's a little bit more robust. We sacrifice a little of accuracy with robustness. So not as accurate as our lab model, but still probably close enough for the types of things we'll be doing in the field. Muscle activity, I'll just include this. It's sort of a blend of physiology and biomechanics, falls into sort of motor control, motor coordination. And we use electromyography. Electromyography is just like an EKG, electrocardiograph, or EEG, electroencephalograph, where that's electrical activity of the brain, electrical activity of the heart. In this case, it's electrical activity of the muscle. There's two types of EMG, and that's surface and indwelling. Surface, just as it sounds, we put sensors on the surface of the skin to measure the electrical activity of the muscle right below those sensors. Indwelling, we actually stick wires in the muscle to be able to measure the electrical activity inside the muscle or for deep muscles. Our lab really specializes in surface EMG. We don't do indwelling EMG. And to make our system more robust, we've been able to get a portable telemetry waterproof EMG system because I like doing swimming research. And this system, you can swim with it. We can do running in the water, which is somewhere where I really started with, and be able to measure muscle activity. So it's pretty slick. And it's wireless. So again, we can use it for a wide range of sports. This was just a study we did looking at muscle activity swimming in different types of wetsuits. So full sleeve wetsuit and a sleeveless wetsuit and buoyancy shorts even. And we were looking at specifically how active the shoulder muscles were during swimming in these different wetsuits. All right, so pulling it all together, you got to select the right tools for what you want. It's easy to spend a lot of money on all these tools. The tools I mentioned, our Speed Lab, it's easily equipped with $400,000, $500,000 worth of equipment. It adds up, cost adds up. And it's important to spend that money in a way that you're getting useful tools that are giving you data that you can then work with. It's not an easy process selecting the right tool. And I've made mistakes in picking the tool that I thought would work and it never panned out. And you're stuck with a tool that didn't work. But we try to do as much research on the instruments before purchasing them to try to minimize that, but it does happen. We also have a lot of instruments that break during our different testing, and the durability is something we try to really pay attention to. But when we're talking about technology and sports science, you have to learn how to operate the equipment. You have to learn how to analyze the data. You have to learn how to critically evaluate the data. I can give you several examples where data were collected and they were just bad data. And the person collecting the data didn't know how to critically evaluate the information, and they were getting a number out of the system, and that number made absolutely no sense. And so then it was a matter of, okay, wait, what's going on? How was this instrument set up? How was it calibrated? All this, you have to backtrack and eventually get to where not only the instrument behaves correctly, but then also train the operator to be able to recognize when you're recording data that are reasonable. And that takes a lot of reading too. Something I advocate with all the students working in the lab is to read everything, because you have to understand the type of data that we're trying to collect and what our target is. And ultimately, you're trying to take in information from all these different instruments, but you, as a sports scientist, want to generate knowledge. Okay, that's it on sport technology. Thanks, everybody.